Electronics, Lesson 7, the particle zoo. Particle zoo is the rather strange name that physicists normally give to the classification of subatomic particles. You need to know how they all fit together, what the properties of each class of particles are, and also just some basic facts about what's going on. So first of all, what are we talking about here? Well, we're talking about all the particles which are smaller than an atom. So an atom, remember, has our electrons and our nucleus with protons and neutrons in it. So that unit is an atom. Anything smaller than that, well, now we're talking about the particle zoo, and we're talking about the individual particles and what they're named after, and what's inside them. So, the first thing we have to do is separate out the two main categories of particles. They are the hadrons and the leptons. The hadrons and the leptons. We'll start with the hadrons. They are made of quarks. So the quarks we have been talking about, anything made of quarks is a hadron. This means they're much, much bigger than the leptons because they're not made of quarks. They're made of things much smaller than quarks. There are two different types of hadron that you need to know about. The first is the baryon. Now this, remember, baryon means heavy. These are the heaviest of all the things within the particle zoo. And they have 3 quarks. So we've already met a bunch of baryons. We've met the proton, up, up, down, the antiproton, anti-up, anti-up, anti-down, the neutron, up, down, down, and the antineutron, anti-up, anti-down, anti-down. These are all different baryons. Baryons, of course, have a baryon number of 1. So, and that number needs to be conserved. So remember, whatever baryon number we start with, we need to end with a similar baryon number. The other type of hadron are the mesons. Now these are also made of quarks, but crucially, they are always a quark and an antiquark. So we say quark-antiquark pair. Therefore, they have a baryon number of 0. Because remember, a quark has a baryon number of +1/3, an antiquark has a baryon number of -1/3, so therefore, overall, they have a baryon number of 0. This is very useful from a conservation law point of view, because it means you can add or subtract mesons, and it's not going to affect your baryon number conservation law. Mesons, of course, are smaller than baryons. They have less mass, because there's only 2 quarks here and 3 quarks there. The defining feature of hadrons, and this is the thing that really sets them apart, is they are affected by the strong force. So remember that strong force that binds things together inside the nucleus, that's going to affect the hadrons. So quarks are affected by the strong force, therefore hadrons are affected by the strong force. They can also be affected by the weak. And we have seen this already, because when we have beta minus and beta plus decay, the flavor of quark inside the baryon changes, which means there must have been the weak force or the weak interaction acting on it. So these are our defining feature of hadrons. Now, let's go over to leptons. Leptons aren't made of quarks. In fact, their defining feature is they are very small. They have not very much mass at all. There are 3 different sorts of lepton that you need to know about. One of them you've already heard a lot about, and that is the electron. We know what electrons are, and remember they're about 1,000th the mass of a baryon. However, there are also muons. Muons I'm going to be talking about a bit more in the next video, but they're slightly more massive leptons that decay into electrons. So they're slightly more massive, and they're going to decay into electrons. So it's basically what an electron is before it becomes an electron. That's a muon. And it is very much a lepton. And then finally, we have neutrinos, which are just high-energy particles, which are mainly there to make the maths work. So we have an electron neutrino and a muon neutrino. There's also an anti-version of all of these. So there's an anti-electron, an anti-electron neutrino, an anti-muon, an anti-muon neutrino. Now, when we're talking about conservation laws, maddeningly, the electron-lepton number has to be tracked separately to the muon-lepton number. So be careful about that. An electron has an electron-lepton number of 1. An electron neutrino has an electron-lepton number of 1. A muon has a muon-lepton number of 1. A muon neutrino has a muon-lepton number of 1. The anti-version of all of these have -1 of their relative thing. This is why, whenever an electron is created, we tend to find an anti-electron neutrino is created, and whenever a positron, remember that's the word for an anti-electron, is created, we tend to have an electron neutrino created. Thus, we tend to create something with an electron-lepton number of 1 and -1 at the same time, so the overall electron-lepton number will remain. Leptons are not affected by the strong force, but they are affected by the weak. So they are affected by the weak interaction, just like the hadrons. You need to know all of this and be able to recreate it on a dime. One thing that's so important is there's very few marks you can get on your physics A-level for simply regurgitating knowledge. But this knowledge here is something that always comes up for a sort of 3-4 mark question. It's something you just need to memorize. We'll be talking more about it in the next video.